All right, hello physicists. We've had a bit of a break because of Labor Day, and let's get right to it. Today we're going to try to um, go over a couple of misconceptions that I've noticed after grading the homework, and then press on and try to introduce electric flux and Gauss's law. Now, this is sort of a come to Jesus moment. Notice we have a test next Friday. What is that test going to be over? Electric forces, so that's Coulomb's law. Electric fields, so electric fields due to a point charge, a line of charge, a charged disk, a charged sheet, stuff like this, all fair game. Then today we're going to do Gauss's law, and soon we're going to do electric potentials. So electric forces, electric fields, electric potentials are basically the three topics of this upcoming test. And I know it's a little scary because we haven't covered some of the stuff that's going to be on the test in a week and a half. But unfortunately, that's the nature of the course. So while you do your homework this week, I would encourage you to start using this formula sheet just to get acquainted with it. If something is not on this formula sheet, it will probably not be on your test. So I was grading homework and I noticed a particular problem that had a lot of wrong answers. And this was from the very first homework. And so it was just about Coulomb's law. So I want to just make sure that we're all on the same page. It says in this figure we've got a particle of charge 2q, that's this one in the middle, is surrounded by a square of charged particles surrounded by either distance d, so that would be like these two particles, or d over 2, so that would be like those two particles, along the perimeter of the square. What are the magnitude and direction of the net electrostatic force on the central particle due to the other particles? Well, in this case, remember we said that if we have a minus charge, it's pulled towards plus charges and away from other minus charges. But if you have it between two, those contributions canceled out. So everyone was pretty good at looking for the contributions that cancel out. You're going to blop, 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 blop. I can cancel, 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 cancel. And then once you got to this final stage, you said, oh, okay, the force is 6 or something like that. You have to, at this point, think about what direction and then what is the magnitude of the force. So in this case, if this distance is d over 2, and this is a plus charge, this is a minus charge, they're asking for the force on this central particle. So our force would be in that direction. There's our force. What's the size of this force? Well, it would be 1 over 4 pi epsilon naught. So that's this whole factor together. We sometimes call that K. That's that 9 times 10 to the 9th approximately. Okay, and then Q1 and Q2, that's going to be 3Q and 2Q. Notice I'm putting them in as the absolute value there, over d over 2 squared. Okay, so you can clean this up some if you want. This is 6, this is over 4, so 1 over 4, the 4 is going to come up here. It's going to cancel out the 4 on the bottom down there. And so you're going to ultimately get q squared over pi epsilon naught d squared. And now I have to think about that's the magnitude, but what's the direction? Well, it's pointing in over to the left. So if I have a standard, x and y type of coordinate system, I would have to put in by hand a minus I hat. Okay, so that's how you would do that problem. Now, I also asked a question for the conceptual question last week. the relationship between fields and forces. And it struck me that there were a number of responses that seemed to say the fields and the forces are the same thing. And I want to try to dispel that idea. Now, a popular way of visualizing the gravitational field, for instance, would be to say, okay, what's happening is kind of like a big stretchy sheet. And that big stretchy sheet is the field in space. And if you have masses in that field, it causes or masses that are positioned in space, that causes the field to stretch out. Then this instructor would throw some marbles on here, and the marbles would roll around on the sheet. Those marbles are experiencing forces that are due to the field at their position. So in this analogy, the field is the sheet, this stretchy sheet is like the field. The big weights are like the charges or the masses that stretch out the field, and the marbles are like the test charges. Now, of course, it's a little more complicated for the case of charges. And the reason it's more complicated is that Q can be either positive or negative. So, what is the relationship between the electric field and the electric force? Well, the electric field is something that's sitting around in space. Okay? In fact, you can think about the electric field as just being a little vector that's at every point in space. It could have a zero magnitude. That would be fine. But it's just a quantity. And then do the electric field and the electric force always push in the same direct, or how do the so to say first, what is the relationship between the electric field and the electric force? It's this. Electric field is an object. This is the object that you're putting in the electric field that has a charge Q that experiences an electric force. So electric field is a different object, this thing hanging out in space, from the object that's experiencing the force. Do the electric field and the electric force always push in the same direction? No. They point in opposite directions if Q is negative, but they do point in the same direction if Q is positive. Does a particular electric field, one say with a magnitude of 10 newtons per coulomb, apply the same amount of force to every particle that sits inside it? No. If you have a bigger charge, you'll get a bigger force. So that was what I was trying to get about with this picture. If you put a particle inside of, in between these charged plates, there's a strong electric field in there. A positive charge would accelerate right, a negative charge would accelerate left as a result of those forces. But we're trying to get away from thinking about the electric charges necessarily, being directly causally connected to the field. The field is just something that is in space. It can be stretched by nearby charges. Okay, so I know that's a little bit of complication because there's some ontology rolled into it. Okay, last week the quiz scores were a bit lower than they were the week before. And so I want to just check what are the questions we had. Well, like this question, which one of the following statements best describes the electric field at a distance r from the electron? Well, what you need to keep in mind here is that the electric field tells you about what direction a plus charge would get pulled, so it gets pulled towards a minus charge. And so an electron is a negative charge, so the electric field is going to have this form. It's going to have this thing is K. KQ, KE over R squared and pointing toward. Okay, so I'm not sure why we had so many people miss this one. Then we had, which one of the following expressions gives the correct relationship between the electric field strength E and distance r from an electric dipole? An electric dipole, remember, is a plus and a minus charge that are separated by some distance little d. and the dipole moment is given by a vector that points from the minus side to the plus side with a magnitude of q times d. Now notice here's your electric dipole field dies off as 1 over r cubed. Okay, so that's this one. And it's also proportional to the dipole moment on the top. Okay, I think a lot of people said E is proportional to R because if you have an infinite line of, actually, I'm not sure. That's really not a good guess. So anyway, something to watch out for. The last one to watch out for is that the potential energy of a dipole sitting in an external field, if the dipole is lined up with the field, it has the lowest amount of potential energy. If it's opposite the electric field, so there's your 180 degrees, it has the highest, and if it's, by convention, we say that if it's perpendicular to the field, it has potential energy of 0. Remember, we can never really detect energies, we can only detect changes in energy. So in this case, the potential of the energy decreases as it swivels and aligns with the field. So we had a fair number of people get this wrong. So this would be 0 degrees. This would be something like, 60 degrees or something like that. Okay, so today we're going to try to introduce electric flux and Gauss's law and do a couple of problems to get us in sort of a feeling of understanding on this stuff. So electric flux is the dot product of the electric field and a vector representing a surface oriented outward with a magnitude equal to the surface area. Okay, so it depends on the magnitude of the electric field, the area of the surface that you're considering, and the angle between them. So I think it's easiest to give an example where we change that angle and see how our flux changes. So for our example, let's use an electric field that's a constant, 4 newtons per coulomb, and in the I hat direction. Okay, and let's use an area that's constant at 3 meters squared. Okay, so in this case, what does it look like if your angle is 0 degrees? Well, let's say here's my electric field. I realize I'm going to run into my head on this on the video. Okay, here's my electric field, 1, 2, 3, 4 newtons per coulomb. And the way I would like to explain this is that here's my area, and it's a little tricky because that area vector, here's the magnitude, we're thinking of this area as a vector that's pointing out of my surface. So here's a electromagnetics textbook. The area of it, the area vector for this surface would be the area of that front pointing out of the top. So it could be pointed in the area vector for this book would be in different directions depending on which way I orient it. So here, the tradition of calling this 0 degrees has this area pointing in the same direction as the electric field. So it's a little confusing because the surface is basically perpendicular to the electric field, but the area vector, by the way that we're writing this, is going to be parallel. So then if we want to find the flux through this surface, it would be the electric field magnitude times the area times the cosine of the angle between them. Okay, so that in this case would be 4 times 3 times cosine of 0. So that would just be 12, 2 Newton meters squared over coulombs. Okay, then what about if we took something like angle equals 60 degrees? Okay, what would that look like? Well, our flux is going to go down, but I want you to picture why that is. Okay, so here's our 0 degrees direction. 60 degrees is going to be something like this. Okay, so there's my 60 degrees. What's happened here is that my surface now is over like this. And the way to picture it is that in this case, fewer electric field lines are going through. So again, I would take 4 times 3, which is 12, times cosine of 60. Okay, cosine of 60 is 1/2, so this would give me 6 Newton meters squared per coulomb. On the other hand, if I took my angle as 90 degrees, then I would have the case where here are my electric field vectors, and then my surface would be oriented essentially parallel, but my area vector, this is my area vector would be perpendicular, and so my flux would be 0. Why is it 0? Because cosine of 90 is 0. And why physically is it 0? Because the electric field vector, the electric field lines are not piercing the surface anymore. So sometimes in your book they'll give you kind of a tricky example like this one. It says the surface shown measures 3.2 millimeters on each side. Okay, so you've got 3.2 millimeters by 3.2 millimeters. So you can go ahead and find the area of that, of one of those sides, which would be 0.0032 meters squared. Okay, divide by 1,000 to do a unit conversion between meters and millimeters. It is immersed in a uniform electric field with a magnitude of 1,800 newtons per coulomb. Okay, 1,800 newtons per coulomb. And with field lines at an angle 35 degrees with a normal at the surface as shown. Okay, now, in a problem like this for your book, I will probably not be this tricky, but notice they are trying to screw you up because the way this is drawn is like this. Okay, so here's the A that they're drawing, and they're giving you the complementary angle. Okay, they're giving you that 35 degrees there. And then if you're looking at the angle between the A and the E, it would be, so 180 minus 35 is 145 degrees. And so if you stuck these together, equals 0.0032 meters squared times 1,800 newtons per coulomb times cosine of 145. Okay, that would give you, that's why they in the textbook example, you'd get a negative on this one. Okay, so this is a subject that has some very clear relevance to our modern society. And one way is that when you have to figure out what direction you want to orient your solar panels, for instance, you want to get those as close to perpendicular to the sun's rays as possible, so they soak up as much of that solar energy as you can. So the sun's path is higher in the sky during the summer and lower in the sky during the winter. That's why it's colder during the winter, is that the angle during that flux allows the ground to soak up less solar energy. And so if you were an engineer who was working on a solar array, you could you'd sort of have to do an analysis. You'd certainly want to get these in the best orientation possible. I've seen some arrays where they also put a little gear to change the direction of the array during the day or during seasons. Okay, so why are we working up towards this? Well, we're working up toward it. Well, we're working up because we want to do examples with Gauss's law. Now, Gauss's law, if you're a physicist, is not a fundamental law. It's a consequence of everything we've set up already, having to do with point charges and so forth. That's kind of a Calc 3 topic. So let's more or less treat it as a law for today. And what does it tell us? It tells us that if we add up the flux over a closed surface, it's directly related to the charge that's enclosed in that surface. Okay? So if I have a surface and the flux, I'm going to have to think about the area vectors on all of those sides. Okay, so this is not always going to be that helpful, but if I consider the charges that are sitting inside of the box, I can relate the electric flux to those charges. And as I'll show you in a couple slides, this can sometimes be super helpful in simplifying certain classes of problems. Now, just to make sure that this has some kind of, passes the smell test at a basic level, let's go ahead and check that it works for just a single charge. So there's my Q, and let's go ahead and draw a surface around this. Okay? Now, because we're drawing a sphere to respect the symmetry of the problem, what we're going to have to actually do is split this sphere into a whole bunch of little areas. Okay? And so the little area vector, there's my dA, is for that small enough surface going to be pointing out just like my electric field vector. Okay, so the electric field vector is pointing straight out, and I've chosen this sphere as my surface just so that I can have the dot product give me a 1. Cosine of 0 degrees is 1. So in this case, my EdA is my flux. So my little d flux, my differential flux element, is going to be E, so that's this size, 1 over 4 pi epsilon naught times Q over, and the radius of this sphere is going to be r. So we're going to have an r squared there. So that's our E, and we're going to have to take that times dA. Now that just gives me the flux through one of those little things. What would I do if I wanted to find the flux through all of the little squares that are on the surface of that sphere? Well, I would have to add up all of the area. Well, how big is the surface area of the sphere? It turns out it's just 4 pi r squared. So in this case, doing that integral, you're doing basically a surface integral over both sides of this, is going to give us an extra factor of 4 pi r squared. So we have 4 pi epsilon naught Q over r squared. And this is going to give me 4 pi r squared when I integrate over those areas. And then what has happened here? Well, it turns out that if I use a really big sphere, I will have a small field. If I use a really small sphere, I'll have a really big field. So these r squareds actually cancel out. The 4 pi also cancels out. In fact, now you're seeing why was that 4 pi included there in the first place. Is for the convenience there, so it would cancel out later on when we did this Gauss's law application. But notice the flux over the whole sphere is q over epsilon naught. Now it turns out this is a more general theorem than this. I've done the most simple example. There's a theorem called the divergence theorem, which has a lot to do with vector calculus, Calc 3 type of stuff. So we won't touch it here. Now, let's just look at a way that you can be clever with Gauss's law. It says a proton is at a distance d over 2 directly above the center of the square of side d. What is the magnitude of the electric flux through the square? Now, if you were going to do this problem directly, it would be pretty tricky because you'd have to split it up into a bunch of little squares, right? So you'd have a dA that's pointing like this way, and then your dE would be pointing out like that. So finding the little fluxes and then doing the surface integral would be quite tough. On the other hand, if we have this Gauss's law, we can think about the Q enclosed if we just put this Q inside of a box right at the middle. Okay? If we do that, we should get the same amount of flux through each one of those sides. And so we can say the epsilon times, there are 6 sides on this thing, 6 times the flux on just one of those. So I'm calling the flux that's coming through here just my flux naught, is going to equal, it's a proton, so its charge is E. Okay, so the flux through one of those surfaces, which would be the same if as what I would get if I actually did this integral with a differential area and so forth. I can say that the flux through just one of those squares would be E, the proton charge, over 6 epsilon naught. Okay, so that's a little bit of a too cute problem, but basically all of the problems that we're going to do with Gauss's law are going to be too cute by half. Now let's look at another example. Let's say that we have a box that we put inside of a constant electric field. Okay, so the electric field is here, and each of these sides has a little area vector pointing out. So there's the area vector for the surface. And so if we want to find the total flux, see our back surface also has an area vector pointing out. We would have to add up the contributions from all 6 of those. Okay, 1, 2, oh, there's one coming out the back too. Okay, so I have 6 sides on my cube. I have area vectors sticking out. Now, if I have a constant field and a closed surface with no extra charge in there, the total flux through all sides must be 0. But let's see how this works. Okay, so on the top and the sides and the bottom, the electric field and the area vectors are going to be perpendicular. So in each one of these, top, sides, bottom, the flux is 0. Okay, so I'm going to put a little 0 by those just to indicate those do not contribute because the angle is perpendicular. On the other hand, back here, our angle is going to equal 180 degrees because this is pointing the opposite direction. This A is aligned with E, so the angle is going to equal 0 degrees. Now these are the only two that contribute in this case. So our total flux, let's call this A1 and A2, is going to be the flux from side 1 plus the flux from side 2. And so in this case it would be E times A times cosine of 180 plus E times A times cosine of 0, whoops, not theta, 0 degrees. So since cosine of 180 is minus 1, this would be minus EA, and then this one would be plus EA, and that would give us 0 Newton meters squared over Coulomb. So okay, so this is another example where Gauss's law works in a little bit of a non-intuitive way because it's hard to think about getting negative fluxes, but it just has to do with the relative angle of the area vector and the electric field vector. Now, I want to show you two of the gold standard examples of Gauss's law. And I'm going to do this after class. No, I'm not. Let's live a little. Okay, so I want to show you how you would find the electric field of a line of charge and an electric field of a sheet of charge just using Gauss's law. Okay, so we've gone from just checking that Gauss's law is consistent, and now we're going to show how it's going to be useful. So for this first example, we've got a line of charge, and this is an infinitely long line of charge, so it doesn't make sense to talk about the total charge on it, which would be infinite. Let's talk about this lambda, which is the charge per meter. Now, I contend that the electric field from this is going to be pointing radially outward because all of the contributions from one side and the other side are going to cancel out. The only ones that are going to add constructively are the ones that are pointing out. So my electric field vectors are pointing out from at all points on this line. And so if I want to construct a surface that's going to be easy to find the the flux contributions from, it's going to look like this. And our little d areas are going to look like this. And so we have our E pointing in the same direction as our d area. Okay, so our little d flux through that cylinder would be E times dA. Now, since this, let's say that the cylinder that we've chosen has a length of L, the sides of this will not contribute because their area vectors are going to be pointing out like that. So because the electric field and the areas for the ends are going to be perpendicular, the dot product is going to be 0. On the other hand, now if we go ahead and integrate over that whole surface, do our surface integral to find the total flux, it is going to just be the area of that whole surface times the electric field. So this whole surface, if this has a distance of r, is going to be the circumference times that length. Okay, so it's going to be E times 2 pi r times L. Now, we might also ask ourselves, well, how much charge is contained in that little cube, or that little cylinder? Well, the enclosed charge is going to be just the charge per unit length times the length. So it's going to be lambda, the charge per unit length, times L, the length. Now remember, Gauss's theorem tells me that if I want to know what the flux is, I just have to take Q enclosed divided by epsilon naught. Okay, so let's do that here. E times 2 pi r L equals Q enclosed lambda L over epsilon naught. So both sides depend on L. I can divide L out of both sides. And what I find now is that the electric field for this line of charge is pointing radially outward with a magnitude of lambda over 2 pi epsilon naught over r. Okay, so that's a pretty slick derivation. This would be quite hard if we were going to add up all the electric field contributions from all of the little dq's. You could, but this is the easier way to do it. On the other hand, let's say that we had a sheet of charge. Now this has a sigma, which is charge per meters squared. In that case, if I had a whole bunch of plus charges spread out here, I would expect the electric field just to be pointing not radially outward, but it would be pointing up and down. Now this is an infinitely large sheet. Now I'm going to do the same thing. Let's introduce a small surface. It extends through here. And I'm going to just contain a little circle in there that has some charge in it. Okay, so again, my little d flux is going to be the top is going to have some area. It's going to be, let me put it this way. Since this electric field is now essentially constant over this whole thing, because it should not depend on anything going either way in the xy direction, because it's an infinitely big sheet. It's going to, if I add up the flux, it's going to essentially be the flux from the top plus the flux from the bottom. Okay, how big is that going to be? Well, however big this area is on the top and bottom, it's going to be E times A on the top, because A is pointing up on the top, E is pointing up on the top, and it's also going to be E times A on the bottom, because the electric field is pointing down, out from the pluses, and A is also pointing down. Okay, my Q enclosed, since I've chosen this just to be a nice right cylinder, is just going to be the charge per unit area times the area. Okay, so where am I going with this? Well, if I want to go ahead and say that my I'm just rewriting Gauss's theorem again here. Here, my total charge is going, or my total flux is going to be 2 times E times A. My Q enclosed is going to be sigma times A over epsilon naught. And here I find the surprising solution that if I have that infinite sheet of two-dimensional charge, the A's cancel out, and my electric field is essentially constant. It doesn't die off with distance. So that's an unusual case. Remember, that's a little different from our disk that was finite in size. So this is a sort of strange imaginary case where this thing is infinitely big. So that works if you're close enough to a disk, it looks like an infinite sheet. So now we have an interesting case where we have our 1 over r cubed. That's our dipole. We have 1 over r squared. That's our point charge. We have 1 over r. That's our line of charge. And now we have no r dependence, just a constant electric field pointing out from the sheet if we have our infinite 2D surface. Okay, so where am I going with this? I am going to a place where we can do problems where we combine these things together. So for instance, we just found this infinite sheet of charge. What we're going to do next time is show how if you have a disk of charge that's cut out of that sheet, you can combine these two electric field contributions to find out what this new situation is where you have, for instance, a missing piece of that electric field distribution. Okay, so we'll do this problem next time. If you want a super challenge, you can see if you can, if you want to try to figure it out yourself, that's okay. But we're going to start our video next time with this. And I think that's enough for today. So what have we done? We've talked about electric flux and Gauss's law. Gauss's law gives us a nice way to calculate the electric field for various examples like a line of charge or a sheet of charge.